pavements. Let's study them. Let's promote them, and let's really get us to a point in the pavement life cycle where we're not reconstructing pavements, but we're just maintaining them and maybe doing some surface treatments and things of that nature. So what is a perpetual pavement? The Asphalt Pavement Alliance defines it as a pavement that is in service for at least 35 years. If we look at it historically, it can only have minimal structural improvement, so less over that 35-year history, less than a 4-inch total AC gain. So this may just be milling and inlaying just to restore the surface as opposed to adding structure over the years. Infrequent resurfacing. So it doesn't qualify as being perpetual if we're going out there more often than every 13 years. And you find lots of pavements that meet this criteria, and I'll show you that in a minute. But this really ties into the sustainability aspect here, that to be sustainable, we can't be out there every 5 to 8 years. It needs to be a longer time in between those rehab or resurfacing cycles in order to be sustainable. And then finally, no deep structural distresses. And these pictures show deep structural distresses where we have the classic alligator fatigue cracking. This is from our NCAT test track here on the left. And these are cracks that are coming from the bottom, and there's really no real way to deal with that other than to go in and remove that material or be really aggressive in terms of overlaying and carefully selecting materials to resist cracks that may propagate from the existing cracking. And then on the right-hand side is what we would call deep structural rutting. And when we see ruts like this, that without that straight edge, we might not recognize it as rutting without seeing that. But usually that is deformation happening deeper in the pavement structure, and that's a sign of deep structural rutting. So we're trying to avoid these two things. And if we do that, then we can resurface, we can do things at the surface to prolong and just get it into this perpetual mode, as opposed to going in and having to do deep structural repairs. So when we think about designing to prevent deep structural distress, and these are a couple of cross sections from our test track where we did have deep structural distress. And you can see here that we have cracks that have initiated at the bottom of the asphalt and have propagated up through the asphalt layers, and we see cracking at the surface, trying to avoid that. And then over here in this cross section where you can see the deep ruts in the wheel paths here, and you can see the various layers, but you can also see, if you look at this bottom string line, you can also see that there's distortion happening down here in this aggregate base, and it's tougher to see, but there's also distortion happening down in the subgrade. The stresses reaching those layers are causing distortion, and to fix that, we really have to do something aggressive, like a full perhaps reconstruction of that cross section. So we're trying to design to prevent it. And how do we go about doing that? Well, back in 2001, there was a TRR circular that was published, and it contained a number of papers, and it really represented the current state of the art, state of the practice thinking on perpetual pavements. And there was a diagram that Dave Newcomb included in his contribution to that TRR that just had sort of a generic perpetual pavement cross section. And in that figure and in his discussion of that cross section, he stressed the need to have a strong pavement foundation, and there's a lot of ways to achieve it. And we're not going to go through those details here today, other than to say there's only so much you can do with asphalt layers above a weak foundation, and so addressing that before you build the pavement is important, and drainage, of course, is part of that. And then above that, when we focus in on the asphalt concrete layers, it's really recognizing that in different parts of the depth or through the depth of the cross section, the pavement, or we're asking those materials to exist in various and different strain regimes and experience different stress levels. Toward the top, where we have a lot of compressive and shear stresses, we want to have high quality, high modulus, rut resistant materials. And at the bottom of the AC, of course, where we get a lot of this tensile stress and strain, a lot of bending action, causing cracks to initiate and propagate to the top, we want to have fatigue resistant materials, or build it just thick enough so that we keep the strain level low enough so we don't have that occurring. And back then he postulated, along with his co-authors, that kind of a range of thicknesses here. And it's interesting, if you look at sort of the minimums, we have 7 plus 1.5, so it's 7.5 inches on the low end, up to about 14 inches on the thick end. And what we've seen over and over again, and I'll show you some cross sections, is Most perpetual pavements for high type pavements, interstates, high volume state routes, things of that nature, they land in this range, somewhere in that 7.5 to 12-inch range. So switching gears now back to the Asphalt Pavement Alliance, back in 2000, I think it was the year 2000, they started awarding and recognizing and awarding pavements that meet these criteria. And the first award category that began 23 years ago were the by performance awards. And these were for existing pavements, all the things I said earlier, at least 35 years old, minimal structural improvements, and infrequent rehab. That's that 13-year cycle. More, and there's lots of them, and I'll show you a schematic or a map that shows all the awards that have been given. And then we have two newer categories that the APA has started just in the last couple of years to promote the idea that we can go out and design a perpetual pavement. So a pavement that is purposefully designed according to the perpetual pavement criteria. If it meets the criteria, you can win this award. And then by conversion, and this is the really the focus of today's webinar, is to zero us in on converting existing pavement infrastructure through rehabilitation into perpetual pavements. And there's a particular category that is very attractive for us to do this conversion. And so we're going to focus on that. But first, I just want to point out that if we look at the by performance award winners, this is through 2021, 164 pavements have been recognized, covering 32 states across the country. And you can see that they represent all parts of the US, all different climates, from Alaska to Florida, and from the Northeast to the West Coast, North, South. They're found everywhere. Some have more documentation available and enables us to identify and award these perpetual pavements. Tennessee currently leads the nation in perpetual award winners. We have some that just have one or two, and the ones that have zero, I suspect that they have those structures there. There's just insufficient records to be able to prove that they meet the perpetual pavement criteria. So again, these show up in all parts of the US. And if we look at perpetual pavement awards by design, these are structures that were identified in 2021 as meeting in new construction, meeting the perpetual design criteria. So if we think about the pavement life cycle here and think about how to be sustainable, we're really coming in here in terms of the materials production in the design phase and construction and getting it into the use phase. And so it's a matter of using the criteria to come up with the pavement cross sections that will meet the perpetual design criteria, knowing that going forward, we'll have a very long life where we'll only ever have to deal with what's going on at the surface of the pavement. And interestingly, if you look at these cross sections, the AC depth range from 9.25 to 14 inches across all these different pavements. And they include an interstate pavement, US routes, some state routes. And this pavement here, this Iowa Route 100, this is a section I'll talk about later, where there's a really interesting study that was done to characterize the life cycle of the pavement in terms of its sustainability. And I'll get into some of the details on that. But the range that we have here is in the range that was put forward in this diagram from 2001, is right in the smack dab middle of that range. If we look at by conversion, what's interesting here is we're really focusing on this part of the life cycle here is the preservation, maintenance, and rehab. And rather than go to an end of life and reconstruction, the idea is, can we convert it from a heavily distressed pavement into a perpetual pavement? And these are all sections that were awarded in 2021 by conversion. And we have some interstate, like an interstate bypass here, a few interstate sections, and some other state routes here. And what's interesting is, again, the depth is a little thinner than the previous, and there's a reason for that, and that is that 4 of the 5 winners were built on top of an existing concrete pavement that fractured slab techniques were applied to, either crack and seat, break and seat, or rubblization to basically convert it into the new pavement foundation, on top of which new AC was constructed. And out of these, the I-5 project I'll be talking about a little bit later, have some data to share with you on that, but it was converted from a badly failed concrete pavement into a perpetual pavement. So again, we'll focus on that in a little bit. So just to summarize our existing perpetual pavements, there's many examples, lots and lots of these award winners covering 32 different states. Many of those were achieved through conservative design using our older empirically based systems. But of course, to be sustainable, we need to optimize the cross section. And part of that is computing maximum layer thicknesses. So if you use existing pavement design systems, like the Astro 93 or ME design of any nature, most of them do not have a check that is built in for maximum pavement thickness. But the nice thing about using perpetual pavement concepts is that we can develop a set of criteria that will cap the thickness so that once we get beyond that, we can simply set that as the maximum, and that can help us with the sustainability aspects, let alone the economic part of it. And finally here, considering existing pavements, and this is structural improvement and or rehab. And again, this is what I'm going to be focusing most of our time on for the next 40 minutes or so. So just for those that aren't familiar with mechanistic empirical pavement design or structural design at all, I just want to highlight how we go about doing ME design and where perpetual pavements fits into that. So ME design begins by guessing at the layer thicknesses and knowing what the properties of the layers are. So this would be like dynamic modulus of the AC layers, and we put in trial thicknesses. We simulate loading events on the pavement structure, and using computer models, we make a prediction about how much stress or strain this axle load or this wheel load causes at the bottom as a predictor for cracking to propagate to the top, knowing all the properties over here. And so we use that as a predictor for cracking. And then we may look at various depths through the pavement structure, compute stress and strain, and maybe deflection, and use that as a predictor for how much rutting may occur through the depth of the structure. There's a lot more to it. There's lots and lots of details, lots of other webinars and reading materials you can dig into related to ME pavement design. But that's the essence of it, is having a mechanistic pavement response prediction and then correlating it through an empirical equation to predict when and how much cracking or rutting or whatever distress is going to show up. Perpetual pavement design follows the same framework. We have a pavement cross section that has layer thicknesses, layer properties, we simulate load events, but now when we make that computation, we're checking it against a maximum value. And that maximum value, we call that the endurance limit, and that is a amount of strain below which damage will not occur. And we can measure this in the laboratory. We've measured it in the field, and this is a real material property. This exists for really all materials, and we can measure it with asphalt concrete materials. But the idea is, if we know what that endurance limit is, we know how much it can handle, we just design the thicknesses such that we keep the strain level just below that endurance limit, and thereby we have reached an optimum pavement design. We can do that both for fatigue cracking and for rutting. So it's key to know what those endurance limits are, because that will dictate then what the layer properties ought to be, or what the layer thicknesses ought to be. So this is some research or some data from the NCAT test track, and one of our former PhD students that is now at Napa, Dr. Richard Willis. This was one of the main things that came out of his doctoral work while he was here at Auburn working at NCAT, was he put together all of these strain distributions for all these different test sections at the test track, and this is showing how much strain they're experiencing, how much tensile strain they're experiencing. That's on the x-axis, and then the vertical scale is the cumulative percentile, so that's like the maximum, the minimum, here in the middle is the average. And he put all this together, and then he grouped the sections by whether they had or did not have bottom-up fatigue cracking, and quite surprisingly and miraculously, what we found was everything on or to the left of this blue curve did not have bottom-up fatigue cracking. Everything on or to the right of the red curve did. And so that established for us, in terms of design criteria, an upper or a maximum distribution. If we keep it below this blue curve, we should have no bottom-up fatigue cracking. And the further away we get from this curve, the more conservative it is. And so, for example, it's kind of hard to see, but this S13 from 2000 almost looks like tick marks on the y-axis, but that's actually a strain distribution. This was one of the original test sections at the test track And it was built 24 inches of asphalt concrete, very thick concrete, asphalt concrete pavement. And it had very little strain, no surprise there, but it was straining so little that we would never have failed it in bottom up fatigue. And in fact, we got the same performance out of this section as we did this section. The difference from here to here is 15 inches of asphalt concrete. It's tremendous. It's a tremendous finding that we had that much conservatism built into those original test sections. But again, the main takeaway from this plot is that we have this upper distribution by which we can do design. So we took that and we said, well, let's look at sections from around the country. Let's get some existing Perpetual Pavement Award winners. And we pulled sections from a variety of different, or from different states, different materials, different subbase and asphalt concrete mix designs and so on. And Dr. Tran at NCAT and I and a few other colleagues worked on this together. And what we found was that when you look at the bottom of the asphalt concrete, what we did is we simulated these sections and compared it to the criteria. And what we have in this plot is kind of the bottom, this red line is the total AC depth. So we had the minimum AC thickness was about 7.5 inches in Montana. And then the maximum was over 21 or almost 22 inches of asphalt concrete. And we examined all of these. We compared all of these against the criteria that I just showed you. And in all cases, we are on or to the left or of that design criteria. And interestingly, the two that I pointed out, Montana being the thinnest, here it was closest. So we would say that's kind of an optimized design. And then Iowa being the thickest was less optimal. And you could argue that they could have built it thinner and still achieved a perpetual pavement. So again, that's an important concept that we came out of the test track, and then we were able to validate with actual long, over 35-year-old pavements from around the country. I haven't talked too much about the vertical strain criteria to control rutting, but 200 microstrain is often used as a design criteria. So we just decided to check that value, and lo and behold, when we ran all those same sections through our simulation software, we ended up with all of them were at or below 200. The one that came close here was the Kentucky cross section. So again, we felt like that was a good validation of those criteria. So the recommended design criteria is to control the strain distribution with these percentiles to control bottom-up fatigue cracking, and then use the 200 microstrain at the 50th percentile to control deep structural rutting. And these ideas are embodied in a few different tools. You can scan that QR code if you like. There's PerRoad and PerRoad Express, and those are available for Windows machines. You can download and install those. And all these ideas that are in PerRoad and everything I just talked about are also in Pave Express, which some of you have used before, but you can also design perpetual pavements within Pave Express, and it just runs through a web browser as opposed to a standalone desktop application. So you're welcome to use those. They're free to use, they're free to download and distribute in the case of PerRoad, and this you just access through your internet browser. So now let's talk about perpetual pavements by conversion and specifically, existing roads. And we have two specific categories. The first is if you have a healthy but structurally deficient pavement, you can just add thickness to meet the design criteria. So this is taking an existing road and just say, okay, well, we were above the endurance limit and we want to convert it into a perpetual before we get into having to do any kind of, deal with distresses and so on. So we're going to overlay it, and we would just use the criteria as I've just described to achieve that. The other, though, that I'll focus more on today is where we have distressed or failing pavements, and we can rehabilitate these pavements into perpetual. And so what we're talking about down here is this preservation part, and rather than reach an end of life, we're just going to short circuit it and do preservation, maintenance, rehab, and get us back into the use phase. So rather than go all the way back around, we're just going to come back over here to use. It's critically important to mitigate existing pavement distresses. If we have cracking, we need to know what kind of cracking it is, how big of a problem it is, and understand that if it's a deep structural problem, that we need to do something about it. If it's a concrete pavement, like I have, this is an asphalt pavement on top here, but whenever you see these very straight lines like this, you know there's concrete slabs lurking underneath. We've got to do something about that slab action. Otherwise, it'll take time, but otherwise those joints or those cracks, whatever they may be, will reflect through. So we need to deal with that distress first, and then we can design according to the performance criteria. So one technique is to use a slab fracturing technique, and this would be crack and seat or break and seat. And later when I talk about the Washington State, the I-5 project, they used a break and seat method, or sorry, crack and seat overlay, what they call CSO. And for those that haven't seen it before, it's basically drop a big guillotine hammer on top of the slab and fracture it clean through. And then basically you remove the slab action, and you now have a really good pavement foundation on which to place your asphalt concrete. And I'll just quickly play a short video just to show you what's happening in this type of rehab. So as I said, it's a guillotine hammer, and it's a mechanism to raise and drop that hammer, and it fractures the slab, and it just marches along. And then we seat it back down with some rollers because the slabs may be a little bit uneven after we go through this process, and then we can overlay. But it essentially turns the concrete slabs into very short slabs that no longer have slab action that cause reflective crack. Another approach is to rubbleize the pavement. So rather than having short slabs, what we do here is basically rubbleize it down into small chunks of broken concrete and aggregate and so on. And there's a couple of approaches here. There's a resonant hammer, and I'll show a quick video of that. Let me go back here a little bit. There we go. So you see that high frequency, low impact. It's resonating at about 44 hertz. And as they're going along, it's just literally shaking the slab apart. And what's left over is just really high quality, once it's been recompacted, high quality base material on which we can, over which we can pave. I think I've got a little more here. This is where they're doing this at a racetrack. Kind of interesting banked turn there. There's a bulldozer up top there with a chain connecting down to the person, to the equipment here running the resonant hammer. And then again, after it's been seeded, we just go back through and pave over the top of it. The other approach is what's called a multi-head breaker, and this is literally just a hammering machine. And so there's weights, and there's no sound with this one, but basically looks like you have lift mechanism. The weight is raised, dropped onto the pavement surface, and it just rolls along, kind of creeps along, and what's left behind is just fractured concrete. I'm not going to get into which ones are more suited for. There's a lot that could be said about when to use various machines and what applications and how to tune it and so on. We're not going to get into any of that, but they can be used successfully in a variety of different situations to fracture the slab and remove that slab action. So now I want to get into just a few case studies that highlight some of these main findings and lend more confidence to using these ideas and approaches and really talk about sustainability. So this first case study, this was an experiment that we did at our NCAT test track for Oklahoma, and this began back in 2006. And Oklahoma DOT was interested in looking at, can we verify these perpetual pavement concepts? Can we intentionally design on the thin side of perpetual, on the thick side of perpetual, and see if there's a difference between them? And then also, is it cost effective? And part of that is being cost effective is it sustainable to do this? So the difference between these two sections, there's a lot of details here, but essentially we had 10 inches of AC on N8, the non-perpetual section, 10 inches of AC and 14 inches of asphalt concrete on the perpetual, same foundation, everything else. So basically evaluating 4 inches of different AC thickness. And what happened was that N8 failed, the non-perpetual section, it basically failed in the first test cycle, about 10 million easels in. We did a mill and inlay. So this is the original cross section, 10 inches here. We did a mill and inlay. We rehabbed it about half the depth, and then this rehab lasted about 3.5 million easels, and then we did a more aggressive mill and inlay where we used highly polymer modified mix. So in this case, what we opted to do, and this was because we were running an experiment, we decided to do this, was we had a lot of cracking down in these layers. And what we decided to do was let's really aggressively put in some really crack resistant materials and see if we can rehab it into a perpetual pavement. And as you'll see, that's what was accomplished. So just to show some performance data, this is roughness on the vertical scale and easels on the horizontal scale, 2 different test cycles. And you can see the perpetual section, it really didn't change roughness over time. If we look at the non-perpetual section, the roughness went up to where we did the rehab, the roughness came back down, and then 3.5 million easels later, it was over 300 inches per mile, very badly distressed pavement. I'll show you a few pictures. And then we did the rehab with a highly polymer modified material to rehab it, and it brought it down, and then it was good for the rest of that test cycle. If we look at rutting, same kind of a story, over 20 million easels. The perpetual section didn't, basically we could say it was less than a 1/4 inch rutting. Over 20 million easels, performed very well. Meanwhile, non-perpetual got up to a 1/2 inch of rutting. We rehabbed it, got up close to a 1/2 inch again. We rehabbed it, and then it was okay. So what did this non-perpetual section look like? Well, we had lots of water standing in the wheel paths. We've got part of the track sliding off of the test track. Whenever you see cones out like this at our test track when we're under traffic during our normal research cycle, you know that something serious is going on because trucks are having to divert around that area or that section to operate safely. There's a close-up of it, literally the pavement sliding off, shearing off of the surface of the test track. So we did a life cycle cost analysis of this, and we extrapolated our data to have a more realistic time horizon. And we looked at the life cycle of each pavement, the non-perpetual versus the perpetual. And interestingly, and as you might expect, when you have 4 inches more of asphalt concrete at the beginning, it's more expensive, and that amounted to a 32% increase in the initial cost. But where the savings come in are all these expensive mill and inlay and trying to repair that non-perpetual section. And what we find if we use the discount rate and life cycle cost analysis type metrics, that perpetual pavement ends up being 26% cheaper from a cost perspective. And that doesn't even get into the sustainability aspects of it, because that section N8 we essentially rebuilt, or we built twice because of the materials that we put in and milling and replacing half of it and then doing that again. We essentially rebuilt that section twice. In terms of material consumption, that was a very costly thing to do from a sustainability aspect. So this perpetual section was a much better option, both just from the straight up cost, but also from a material standpoint. The next one I want to talk about is the case study where we did a cold central plant recycled experiment at the test track. And this is something that Virginia DOT has really been a national leader in this area. And the VTRC and the researchers there, like Dr. Brian Diefendorfer and some of his colleagues there, are really actively pursuing this due to the massive amounts of RAP that they have available in some parts of Virginia, and looking at ways of using that resource and thinking of it as a resource that they have available and putting it into pavements. And so this experiment we did started back in 2012, and it began with us doing what I'll call a pseudo full depth reclamation. We didn't go through the asphalt concrete, but we went through the existing ag base and down into the subgrade. Basically did an FDR-like approach on about 8 inches of unbound material and stabilized it in place. And that's what's going on here. Is that's the reclaimer, where we're chewing up the material, adding some cement and water and stabilizing agent and putting it back down. And then on top of that, we placed where we had a milling operation on different test sections, fractionated the RAP, ran the RAP through a CCPR, or basically a portable foaming machine to mix it up. So we had the RAP and the binding agent. So we had foamed asphalt. We had essentially, it was nearly 100% RAP is in the CCPR layer, and then conventional paving. And so we're using this CCPR layer on top of the stabilized layer as an asphalt bound base, but it's nearly 100% recycled material. Obviously a very sustainable thing to be doing. And what we found, and quite to our surprise, is we built these 3 test sections and we got very similar performance between these sections that are using all this recycled material. When you look at this, the CCPR here, we've got 5 inches, 5 inches, 5 inches roughly of these materials. It's nearly half of that AC depth is made up of this nearly 100% recycled material. We got very similar performance between these sections and sections that we built with all virgin materials as part of the 2003 test track that that we knew to be perpetual. And so it's really interesting when you start looking at this is that we can use these more sustainable approaches to achieve the same performance as these perpetual pavements using virgin materials. And on top of that, we're also, not only do we have this recycled material here, but you can think of this stabilized base, this in-place stabilization. This is essentially recycled material as well. So that's over like 3/4 of this pavement cross section is made up of recycled and reclaimed material. So in terms of and comparing performance between all of these, we had some minor cracking that we saw in the 2003 sections. That it was not bottom-up fatigue cracking. We didn't see any cracking at the surface in section S12. S12 again was the one with the stabilized foundation. And we had minor cracking that showed up in section N4. This was this section after 30 million easels. So it performed very well. And we had very minor cracking. And this section is still in service. We're approaching now 45 million easels on this section. It's performing very well. And the cracking, depending on the day, when you go out there, you may or may not be able to see it. It's very tight, and tend to see it in colder weather when it's a little damp out. You can see water is collected in some of the hairline cracks. We have taken section S12 out of service to make way for newer test sections, new experiments. But as part of that removal process, we wanted to get a look at what was going on down in that stabilized foundation. It's really interesting. We cut open some trenches, and to my surprise, maybe not everybody's surprise, but to my surprise, we saw a lot of cracking in this. This is all stabilized. That was the in-depth stabilization. We saw a lot of cracking there. We cut cores and so on. This crack here, this is essentially right along here in the wheel path. And you can see the crack is running along the length of the wheel path. And you might think, given the nature of this crack, and if we zoom in on it, I fully expected to see that on top of this crack, we would see some reflection cracking going up through the asphalt concrete. In fact, this is the CCPR layer. We didn't see that. And we cut cores on top of these cracks, and it was a working crack. It was cracked all the way through. So they were full depth cracks through that cement stabilized layer, and yet somehow they did not propagate up through that CCPR. We're still studying this. The CCPR is a different kind of a thing. I've heard Dr. Diefendorfer talk about it as, you know, that the foamed asphalt that's in with the wrap is sort of like spot welding particles together. It's a good way to think about it, but it has a different kind of cracking resistance. I think had we put more of a normal AC on top of this, we might have seen or something that wasn't spot welded, we might have seen cracking propagate through this. If we look at the rutting performance, the black series, the dots, the small and large dots, that's the perpetual pavements, the 2003 sections that we knew to be perpetual. And you see nearly identical performance between those sections and these much more sustainable sections using the CCPR and the stabilized base layer. Look at ride quality, again, very similar performance over 30 million easels. This is change in IRI, so it bounces around here. But essentially, we're, you know, after 30 million easels, we were within about 10 inches per mile of where we started. So really no change in roughness over that time. Look at the strain responses. This is where it gets really interesting. That stabilized layer, that's the green series here. What we're seeing is the effect of having a restraining layer that's not allowing the pavement to bend very much, keeps the strain levels very, very low. And that's the strain level that's inside of the AC layer. So it doesn't bend very much, though we might have some joint movement, or not joint, but crack movement from the cement stabilized layer, but it didn't propagate through. And if we look at it in this fashion, you can see that, again, the effect of that stabilized base that was stabilized in place has a very moderating effect on strain. This is versus temperature. So really not a big change in strain level versus temperature over those 3 test cycles. Whereas we see a much more traditional looking curve. We see this on a lot of conventional pavements that don't have CCPR in them at our test track, where it goes up kind of exponentially. So how do these stack up against the design criteria, these 3 sections? Well, the one that had very low strain levels, no surprise here, the stabilized base, it is to the left of the design criteria. So that one definitely checks that box. Interestingly, the one that is still in service, the section N4, is well to the right, or well exceeds that limit, and yet we don't see cracking in it. So that leads us to believe we may need to rethink the criteria for these CCPR. This would be very conservative to use for this test section, because we're just not seeing the kind of cracking that we would expect. And when we've seen curves like this in other sections of the track, they have bottom-up fatigue cracking. So we did an economic analysis. This was in a TRB paper from a few years ago, where we got actual bid or from actual projects from VDOT for the different materials that were used, and then costed it out. And interestingly, when you look at it, the least expensive section that we had out there was section N4. This is the one that had 4 inches of AC over the CCPR, came in at $37 per square yard, and that's 34% lower cost than the 2003 sections. You can see those costs here. But interestingly, even the one that has the cement stabilized layer is cheaper than the other 2 less sustainable options. And if we look at, if we normalize the data for how much we get per structural number, if we put it in that context, then this one comes out the cheapest at $8.18, and a pretty good savings there as well, 31% less expensive. So the epilogue on this particular experiment is VDOT is moving full steam ahead with using CCPR on their network. And a good example of it is I-84 near Williamsburg. It was built in 2018, about a 7-mile section. They used 200,000 tons of RAP on this section. And this schematic over here shows the original and the recycled, like what they were going to build or what the normal design would be. And then using FDR here down in the bottom, and then they put in an open graded drainage layer, CCPR and AC. But this is their recycled, like the more recycled section, and it cut the cost by more than half. They used 200,000 tons of RAP in the project. 75% of that cross section is recycled. It's remarkable. They estimated 50% fewer greenhouse gases in terms of a sustainability metric using this versus the original, and a $10 million savings. So to me, this is a really powerful case study of how sustainable this perpetual section can be, or a perpetual section can be. Let's talk about a few other cases here. So I mentioned earlier the I-5 project. This is in Washington State. This is south of Seattle, near the Seattle airport. This was awarded in 2021. This is the most heavily used interstate in Washington. And David Gant from Washington Asphalt Pavement Association, as I have down here, shared this information with me. Most heavily used interstate in Washington. Was an old concrete pavement. They had 20 years of the last 20 years rehab projects and all the things that you expect to see in a deteriorating concrete pavement. Panel replacement, dowel retrofit, all the whole menu of things was being done to it. And basically, Washington State DOT got to a point where it's not really cost effective to continue to rehab it. Ride quality was getting unacceptable, and they were continuing to have deterioration on the pavement section. And so they went in and resurfaced it in 2015 using cracked seat and overlay, or CSO, and basically have now a composite pavement that meets the perpetual pavement design criteria. And this is just to show you where it's located. Just a few, picture of what the pavement looked like, where they've tried to do some repair work, but it is really difficult to maintain it. It was reported as having some dangerous patch sections where it's very rough. This is the cross section, and they have the original pavement, 9 inches of jointed plain concrete, over 7 inches of crushed rock. And then this is the cross section coming up above that. And essentially, if you add up those layers and so on, what you get to is a little over 8 inches of AC on top of the fractured slab. They did the crack seed and overlay. So again, it's right in that ballpark. We're not talking about a 20-inch pavement to mitigate this. They rubble or they crack seed and overlay, cracking this slab and then building on top of it. The way they went about doing this is they would basically do weekend closures, very heavily trafficked interstate weekend closures. This is some information about the crack seed and overlay. Basically took the 12 by 15 foot slabs, broke it down into 4 by 6 foot slabs, and making sure that it is cracked all the way through. That's really important to remove the slab action, and then seeding the smaller slabs back into the supporting material underneath it, and then paving on top of it as you normally would. And so this is really getting into this part down here is this, the preservation, maintenance, and really rehab is what's going on there. This is just a picture from the project. You can see the marks from the hammer, the guillotine that struck it as it marched along here. And then now here they're out paving. And this is just the completed project. So the crack seed and overlay southbound on I-5 looks like a beautiful new asphalt pavement, and also southbound there. I'm running a little bit short of time, so I'm not going to play the video, but if you're interested in seeing more details about this project, you can Google the Revive I-5. It's available on YouTube, where they talk about the process and have more pictures and things. You're welcome to look at that. But I do want to point out down here is that when Washington State does their LCCA on these types of projects, that they show more than 25% cost savings when they do a crack seed and overlay instead of reconstruction. And again, this is a much more sustainable because you're using all those materials that are already in place. You're just rubbleizing, you're cracking and seeding it or whatever you're doing, and then you're leaving it in place. You're not hauling it away. You're not having to do anything other than just change its properties as it sits there in the existing roadway. And finally, I want to talk about this case study that was done in 2016, and the study authors were Gerardo Flinch from Virginia Tech, Yolt Meyer from the Wright Environment, and Kurt Smith from AppTech, and you may know these people. But this was the project that I mentioned earlier that was one of the award winners, one of the by design award winners. And it's Iowa State Highway 100, and you can read more about it in this FHWA document. I've got the source here, but if you look for that document, you'll find it. But it was really interesting that they went through and documented and quantified some very specific sustainability metrics that I'll go through here in a minute. But just to tell you about this particular project, so this was 12.5 inches of AC over 15.5 inches of modified subbase. And this 12.5 inches of AC, that is in that range that I talked about earlier, about 7.5 to 14 inches is right toward that upper level of that range. And interestingly, in this cross section, the upper lifts here, as you can see, the wrap content for the surface, intermediate, and upper base, they're running 12 to 15% wrap, so they've got that there. The bottom mix, they didn't put any wrap into it because they wanted to design it to be more fatigue resistant, and they also designed it at a lower lab design air voids. And this is one of the techniques if you're trying to design a fatigue resistant mix. If you design it for a lower air void content, that'll basically force you to have more asphalt cement in the mix and make it more fatigue resistant. So no wrap there. And then this 15.5 inches of modified subbase, they used 50% wrap and 50% virgin limestone were blended together to make that subbase. So this has a lot of recycled content in this cross section. And again, from a sustainability point of view, this is really important, is they went through, the authors of this study went through and quantified from the conventional design, not being perpetual, and then the perpetual alternative, which is this cross section. They went through and quantified how much savings they got from these very specific measures of sustainability. So ozone depletion, 20% less. global warming, about 19% less, and so on. Smog, ecotoxicity, fossil fuel depletion, that's a really important one, of course, 20%. Water resource depletion, about 25% less. So in every single category, this perpetual pavement design was better at each of these measures of sustainability. So to wrap up this webinar, before we get to questions, perpetual pavements by this point, they're widely recognized across the U.S. We typically focus on existing pavements or new construction, but as I pointed out today, we really can be thinking about our existing highway infrastructure in ways that we can rehabilitate it into being perpetual, and we call that by conversion. It's critically important, though, to consider the existing distresses during the design and then ultimately the construction phase to make sure that we're handling that, because if we don't handle it, we're just potentially building a relatively thick pavement that's going to have reflective cracks, for example. So we need to be careful about that, but we can do it. And there's lots of examples of that being done successfully. We can achieve many sustainability goals in the pavement life cycle. I've highlighted some of them here today. But again, the kind of stressing this idea that once we get into perpetual pavement, then we're just in this use and rehab or preservation, maintenance, and rehab part of the cycle. It's kind of a mini cycle rather than having end of life in these other parts. And that just naturally makes them more sustainable over time. And finally, and maybe one of the most important measures of sustainability is how cost effective it is. And perpetual pavements we see time and again are cost effective pavements, especially if we're using older design systems that are overly conservative. We can use perpetual concepts to cap a thickness and make it way more cost effective, especially on high traffic routes. And so with that, I want to again thank you all for being here today and thank the APA for putting this on. I really appreciate them organizing this. And I guess we'll open it up for questions and discussion. And I see that there's a number of them there.